first thing that we wanted to talk about as we work our way through all the different types of responses to the breach was the geological responses. And Dr. Charles Flagg is going to fill us in about that as our first speaker in that section this morning. Charlie is one of the first people who has been out looking at the breach and trying to characterize its morphology. He was out getting aerial photographs very shortly after the breach occurred. And he approached New York Sea Grant for some funding. I think it worked that way, that we didn't find you, you found us, but we started some very early funding to get him off the ground with that. And then that was rapidly picked up by DEC and the National Park Service, and the National Park Service continues to fund his work looking at the evolution and dynamics of the breach area. So that's the focus of his talk this morning. Charlie.
Okay. Thank you very much. All right. So I live right across from the breach, and so the Hurricane Sandy was a big event, obviously. And I have a bunch of friends who are pilots, and so within 2 or 3 days of the inlet, we were able to, after they cleared a runway at Brookhaven, we were able to take a flight. So we've been monitoring the evolution of this inlet ever since. We also had for other reasons, the Great South Bay was already instrumented in, with a series of sensors around the perimeter of the bay and a buoy in the center. So this is one of the few instances of a barrier island breach where we have information prior to the breach that can be compared with the information that we've collected after the breach. And so this turned out to be a vital change from the usual practice where you scurry around afterwards and then hypothesize about what was going on beforehand. So, as you're all aware, this area of the barrier island along Long Island has experienced a series of breaches over the last 2 or 3 centuries. And the ones that are listed here, they all lasted a substantial period of time, typically on the order of 50 or 60 years. The old Inlet breach, the one that is sort of in the history books, lasted from 1763 into 1825, so it's a 60-year period. And it is just to the west of where the new inlet is. The current breach is right about there. So let's see if I can do this. This is a animation of the Hurricane Sandy from the Penn State hindcast modeling, and with a little luck we can get this thing to run. Okay, so the thing about Sandy was that it was huge. It was huge and it was slow moving. And so the distance between Florida and Cape Hatteras is something on the order of 2,000 kilometers. So this guy is 1,500 kilometers across. The distance between Cape Hatteras and Cape Cod is about 1,000 kilometers. So here, just as this thing is passing Cape Hatteras, it's already impacting the entire area. The scale over there to the right gives you the speed in meters per second, and it goes up to 45 meters per second, but that's about 90 knots. So, you know, hurricanes are, in terms of knots, hurricane winds are about 62 or 65 knots. So this thing is a hurricane, but only just sort of. And so as it's coming in, you can see that it's affecting the whole mid-Atlantic bight, and then it takes this weird left-hand turn, as everybody's aware. All right, so this is the buoy that's just south of Long Island. This is 44025, the NDBO buoy. And here we have wind speed, a wave height, and atmospheric pressure at the buoy. Wind speeds are reach a maximum of just short of 50 knots, and so even in the middle of the mid-Atlantic Bight, this thing was never really a hurricane. So the real impact here is that there's two parts. One is that it took a long time, so it blew and set up the coast for a long period of time, and so there was a long time for the waves to set up. Wave heights were on the order of 30 feet. These maximum wave heights. This is the average of the 1/3 highest waves. So 30 feet is sort of a conservative estimate of the maximum height of the waves. The pressure drop here from normal is 40 millibars. Well, the inverted barometer effect says that would add 4/10 of a meter to the storm surge that's purely wind driven. So all these guys are affecting what's going to happen. So this is a typical schematic of what's going on as a result of a strong westward wind. So it's heading toward New York. Water piles up against the coast, against the dunes. And on top of that are some of these huge waves. And so they overtop. And when they overtop, they have this enormous height difference in the water on either side. And it was at least 2 meters and probably more like 3 or 4. The water here in Belport Bay dropped by a half a meter before the breach. And the water on the outside was at least 2 meters high. So something on the order of 2 to 3 meters height difference between them. And so it just, once you knocked a small hole, that height difference quickly eroded it. So as I said, we have this observatory that's been in the water since about 2005. The instruments I'll be talking about are the ones at Belport, Tanner Park, and the USGS site in Lindenhurst, which I think is about here, and also from our buoy in the center of the bay. This shows, I got a couple of diagrams. They're a little busy, but they show what's going on as the hurricane, as the breach occurred. So the black line is the water levels in the ocean. It's the average between Sandy Hook and Montauk. So relative to mean water level, it's about 2.5 meters above mean water level. Lindenhurst to the western end of the bay is its maximum is just short of 2 meters above its mean. Belport is this red line here. And so what you see is a very typical response of the bay. When the winds are blowing down the bay, the water in the bay immediately responds to the wind. Within an hour, there's a setup typically toward the west when we have these nor'easters or hurricanes. So that is why as the wind increases, the slope between Belport and Lindenhurst increases, and you can see that it reaches a maximum. And then there's a reversal in Belport, and the water level begins to increase. It happens at the same time. Well, the usual thing is when Belport's water level drops, the creeks drain into the bay, and since the sensor is right near the shore, you see a drop in salinity. And then with the breach, there was this enormous jump in salinity, this dotted dashed line here. The next, it's a little more complicated than that, because this next picture, now this is really busy, and I apologize, but it's the only way to show all the timing of all these things together. Top panel shows the winds. The blue line is the wind speed in knots at the Great South Bay buoy. So in the center of the bay. The red line shows the direction from which the wind is coming. So this is a typical nor'easter coming from about 45 degrees. And just as the wind reached a maximum, the direction changed, rotated about 145 degrees. So it went from northeast to south. Down here at the bottom, this is the detided water levels at Bellport in the blue, Lindenhurst, Forge River in black, and then the green thing is the difference between Lindenhurst and Bellport, and the pink line is salinity. If we focus our attention sort of here, well, as the storm came in, the difference between Bellport and Lindenhurst, at first everybody came up, and then the wind started to really crank, and we get this setup down toward the west. And so the difference between Bellport and Lindenhurst is increasing. That's this green line. And it reaches the maximum just as the winds reach their maximum. And then as the winds rotate, the water level difference between of the eastern and western end of the bay drops precipitously. And at the same time, Bellport's water level is actually rising. Now, a significant part of this early rise in water level was simply the change in slope in the bay. So we went from a situation where the Lindenhurst was more than a meter higher than Bellport, and then the bay relaxed as the wind rotated, and so part of Bellport's increase in water level was simply the fact that the bay went flat. And as you can see here, the bay is flat all during this time. It doesn't mean it's at the same, low water level. The whole bay is up together. And so, and then the rest of this increase at Bellport and the continued rise in Forge River and Lindenhurst is due to the fact that the ocean is coming up. And then this long tail is the ocean water that was in the bay is now trying to escape through the inlets. And so the salinity jump happens after Bellport is actually beginning to recover a bit. And so this is when the breach occurs. Now, the breach is 2 kilometers away from Bellport, so there is some sort of a delay, but the winds were out of the south at this point, so it blew it right across the bay, lickety-split. So we've been taking these aerial photographs. Early on, they were sort of obliques, and then we figured out how to take vertical pictures, and we put a video camera on the struts, and we'd fly a zigzag pattern over the breach. And so we've generated a bunch of pictures like these. This is the latest one in October 30th, and you can come up and take a good gander at it. But these are all on the website. So this is what the breach area looked like prior to the breach. This is the old inlet dock and the boardwalk over to the old inlet beach area. This is Pelican Island and the Pattersquash Gun Club's house that's there. This is John Boyle and Ridge Island, and this is the actual old inlet. As you can see, it's a considerable distance from the present breach. The breach happened right through here. This is an old area where boats were tied up over the night when there was beach clubs over here. And the breach actually happened right in here, and you'll see in the next picture, which is from the USGS LiDAR survey, that this is a low point in the dunes. There's higher dunes to the east and to the west. So this is the LiDAR survey showing where the breach occurred, and so right through that cut for the little boat, and right through this hole in the dune system. So this is what it looked like 3 days after the breach. The dock has been cut from the island. There's a lot of the sand that used to be here is now sort of spread over here. Pelican Island has accreted some sand. the breach is also sort of essentially straight across the island. This is, to give you an idea, this is 2 years after the breach. This is October 30. This is the same picture that's on the wall. And so initially that the breach happened right about here, and it was these ticks down here at the bottom, if you guys can still see them, are 100 meters. And the breach at the beginning was about 30 or 40 meters across. So it was relatively small, and it was straight across. As you can see, over the last 2 years, the breach has widened and spread to the west as well. Okay, let's see. Another. Let's see, let's do this. Okay, we've Mark Lang has set up a KML file for Google Earth, and you can download this from our website, and it's very handy to be able to look at the changes. So these aerial photographs have we've taken them about once a month since March of 2013, and so you can see the evolution of the inlet. So here we are. This is like 4 months after the breach. The main channel is essentially straight through. This was, the channel at one point, the main channel was right here. It impacted the Pelican Island, and it actually eroded underneath the house and then floated it off. So at this point, this is the gun club's house. And so it was an ephemeral sort of a thing. Anyway, so if we move along, here's in April, you can see what's happening in particular on the west side. We have this development of a spit on the west side, and it cuts off the west channel, which flows to the west, and concentrates the flow to the east. And as you can see, that happens. Okay, so here we are in July, August, September. That spit extends up toward Pelican Island. And here we are in November, December, and then in January, a northwest wind event came through that was really strong for several days. Winds came in from the west and eroded that spit. And so that seems to be the sort of seasonal character, and we'll see that again this year. The other important thing was that the whole thing is eroding in this direction. The inlet used to be over here, and now it's moved a lot, and there's substantial erosion here on the southwest corner of the inlet. You can just see the development and the spread of the flood delta. These lines are all nominally in the same place. So this delta, which looks like sort of like a cauliflower, was initially sort of in here, and now it's spreading, and it's spreading to the north and as well as to the west. So this is in July of this year. No, I'm sorry. This is in March of this year and May. And notice that the spit has reformed. And then there was an event during the summer that sort of eroded that spit almost completely. And so this is the this is the late August photo. This is at the end of September, and this is what it looks like as of about 2 weeks ago. So the spit has reformed. There's been a certain amount of filling in over here. The main thing that has happened is that this channel has really well developed, and there's about 4 meters of water in here. The maximum depths we've seen here are about 6, but it typically, or 7, but it's typically somewhere between 5 and 6. I'll show you that in a moment. But these This channel is well developed. There is some shallows here, but at high tide, most little boats can get across there. Okay. Let's see if I can get this guy back. Okay, so we've been doing some bathymetric surveying of the inlet, and first time we were a little under equipped, and we've since been using Mike Frisk's little skiff, which is generally okay unless you get out toward the ebb shoal, in which case the combers get a little scary, and we've nearly pitch poled once. So we're much more careful now. This is the kind of survey we've been trying to do with that boat. A bunch of zigzags across the channel and a few in and outs. And then as this area has become bigger and more important, we've been trying to concentrate on that. And here we are surveying out the main channel. Right now, our charge is to survey this whole back bay area. Now, some of this stuff, during the summer, people bring their little boats here. They beach them on these little shoals and put sunshades and chaise longues on them and have their beer parties. So this is really shallow. So we're looking for a shallow system, and so we're in the process of getting a jet ski, we think, and we're going to equip it with Rogers bathymetric equipment, and we'll survey that area. So this is what across the inlet, the profiles across the narrowest part of the breach look like. And so I'm not going to show them all. I'll show you sort of a subsample. But it started out less than 2 meters deep. This was in December, so this is a month and a half after the breach was formed. Down here, the vertical bars are at 50 meters apart, and this is the depths are in meters. And so you can see that it's getting bigger. It's moving to the west. And that actually was the deepest we've seen. This is in February. Oops, wrong way. But then it seems to have more typically shallowed, and first it moved to the west, and then it has moved back. This is the latest profile. It was in early October. Notice the difference in cross-sectional area from May of 2014 to October of 2014. It's the cross-sectional area has increased by about 50%. This is a timeline of the cross-sectional area starting from December. So initially it was only about 100 meters square, ramped up fairly quickly to somewhere between 300 and 400 meters, and maintained that for quite a long time. And then, so this is 2014, so this is May of 2014, June. So something happened in between, and we weren't there. And the cross-sectional area seems to be now between 500 and 600. So it's increased by something perhaps of 50%. To give you some idea about the size, if we assume that it was 400 meters squared, Fire Island Inlet is about 4,000, Mauritius is about 800. The inlet is somewhere on the order of 8 to 12%, maybe is a little bit more now, of the cross-sectional area of the two major inlets to the area. So in terms of the evolution of the inlet, this is where we stand at this point. So if anybody's got any questions, that'd be fine.
I was just about to hold up the 2-minute sign, but you're right on schedule.
Okay, good.
Any questions for Charlie about the formation of the inlet and how it's been changing over time? Images, Chris?
Charlie, given the current morphology
I mean, is there a mean flow?
To the east or to the west from that inlet?
Well, looking over here, the main connection with the bay is through this sort of northwest, southeast channel, and at this point, and it may change in the next few months as these northwest blows happen. This spit has basically cut off the easy connection to the west. So this is the main connection. So actually, we don't know how this melds into the current system in the bay itself. In general, tidal currents in Belport Bay are sort of non-existent. That's probably not the case anymore. Our numerical model, which Dongming Wang worked on as a student, is now pretty sophisticated, but it is of the original system prior to the breach. So we have a really good idea about what's going on prior to the breach. We have a new graduate student, Claudia Heinrichs, who's going to be working on adapting that model to include the breach, and we'll have a better idea about what the circulation pattern is and the changes in the residence times and so forth. Yeah, so that's sort of where we stand.
Okay, we have a couple in the back, Jim.
Yeah, have you done any sediment budget analysis, and can you tell us what the shoaling rates and amounts are for the offshore bars and the interior bars?
No. One of the reasons we want to do the bathymetric survey on the inside is to figure out exactly how much sand has arrived. We do have surveys. Roger Flood did a survey there prior to the breach, so we sort of know where the baseline is. And but doing the bathymetric survey over the shallows hasn't been possible with the equipment we've had, so we're working on that. So, and the USGS is doing the offshore part. They have a duck, which is one of these amphibious vehicles that they're using to do the offshore part. So,
And that'll be part of the next speaker.
yeah.
Charlie, the last slide you indicated that now with the increased cross-sectional area, it represented 10% when compared to Fire Island and Mauritius. And I think in one of your earlier talks, you estimated about 4 to 5% of the volume of water going into the Great South Bay was from that. Now, has the volume of water exchange at Old Inlet increased proportionally to that increase in cross-sectional area, or is it about the same?
My assumption is that yes, that's true. But we haven't done another ADCP survey there. That at this point, I think that's the responsibility for that has been shifted over to USGS. So we'll see what they've got to say.
Actually, I could just speak to that quickly. I was going to just make a comment that the measurements of peak ebb and flood discharge under spring conditions match the cross-sectional area changes really well. The measurements that USGS collected in June and October of 2014 show about a 50% increase in the peak discharge through the breach on ebb and flood conditions at the time of the peak.
Okay.
50% change from what to what?
Increase from about mid-upper teens, 15 to 20,000 cubic feet per second to about 25 to 30,000 cubic feet per second.
We deal in meters.
I know.
Sorry.
Okay, any others? Great.